Before moving on to the lecture, I'd like to acknowledge all of the positive comments and constructive comments and criticisms that I'm receiving from everyone on the course. These things develop over time, and may not be able to get many changes in to benefit you, but we're all committed to benefiting others, and someone may not even be born yet. Hopefully it doesn't take me that long to get these improved. In addition, you'll see another email that I excerpted from one of the students in the class who's an expert in the area of birthing, and you'll see some very nice information, more detailed information about the previous lecture, Lecture 13. And anyone with any information or corrections in my lecture is, I urge you to send a response to me. You can send it, copy everyone as well, especially if you're kind of being nice about it. If you want to be nasty, just send it to me. No need to open nasties for discussion. You're welcome to make contributions and corrections at any time. Certainly, that's what makes this course, especially through the WebCT, really tremendous. So today we're going to talk about multiple births, and we begin with an overview. Obviously, the human female reproductive system isn't designed to have multiple births. We know there are some species that give birth to many, many offspring, and the system is designed for that. Anytime there is more than one embryo developing to a fetus, the risk is going to increase. And we always hear these terms, morbidity and mortality. Morbidity has to do with survivability, of course. There's typically a survival, but some compromise of form, shape, function, metabolism, and so on and so forth, or pathology. Mortality obviously has to do with the termination of the organism, or death. So the multiple births are more common now because there are human interventions that promote multiple ovulations and so on and so forth. So hormone treatments and in vitro technology, fertilization technology has contributed to these aberrant statistics. The frequency typically in the population of twins is 1 out of 85. Triplets, as you see, 1 over 8,100 or 90 squared. Quadruplets just go up in multiples of 90 up through the quintuplets. So under normal conditions, these, if you exclude the data from the human intervention, those are the statistics. So we all know that there's dizygotic and monozygotic twins. The dizygotic are called fraternal, as we know, and this is an instance where there would be 2 ovulations and both would be fertilized. Therefore, both would have a unique genetic makeup. So these are not the identical twins, they are the fraternal or dizygotic twins. So this accounts for about 2/3 of all the twins. And the rate of these types of twins, the dizygotic, do increase with the maternal age. In other words, we would assume a conclusion from that statement to be that the frequency of multiple ovulations can increase with aging of the ovaries in the human organism within which they're contained, I guess, right? So there is a difference based upon ethnicity and race, more common in blacks than in Caucasians, than in Asians. And there's also a tendency for this to seem as an inherited trait, in that there is a predisposition in families for this to occur. So obviously, human female biological systems in some individuals are more likely to have multiple ovulations in one cycle. So we always these will always have 2 amnions and 2 chorions, but they might have either 1 fused or 2 separate placentas. So we'll look at a few illustrations to see how this might happen. This illustration is figure 727. Just checking that it's visible on the entire screen. And we'll look at a couple of different panels. Panel A is where the blastocysts implant separately. We'll see what occurs and how things appear when that happens. And then in panel B, a subsequent one, we'll see what happens when the blastocysts implant closer together. And obviously we're focusing on what happens with the placenta, the chorion, and the amnion. So in this first case of panel A, the 2 separate concepces, the ova that were fertilized and go on to this 2-cell stage here on ultimately into the intrauterine cavity as 2 separate blastocysts. They implant, they're showing in this case pretty close to each other, kind of deep in the myometrium, but we'll allow the illustrative purposes there. But they are separated from each other when they are embedded in the endometrium, so the developing placenta from the trophoblastic cells are unlikely to fuse or have any other such events. So if we look at a more advanced stage of this, we see the 2 separate fetuses, obviously in their own amniotic sacs, and there is a separation between the chorionic sacs. They're separated. Then at a higher magnification at the point of implantation into the endometrium, we see that there are 2 chorions and 2 amnions. The amniotic sacs are shown in the blue. So there'll be different variations in the placenta and the chorion and amnions, obviously, as we proceed to the different discussions. In this case, panel B, again, it's the same process up to the point of implantation, and they are in quite close proximity to each other. And what happens is the chorionic sacs will become fused such that when we look at higher magnification, there will be still 2 amniotic sacs, 2 separate amniotic cavities, and the 2 chorions will be fused together. So there originally are 2 separate and distinct chorions, but the cells are just close enough to each other where they intermingle. Thus, we can take a close look at this table 7.1, showing the frequencies of the types of placentas and fetal membranes in both the monozygotic and the dizygotic twins. I know we haven't discussed the monozygotic twins yet, but we will start with this table and then go on to the details in a moment. So we see in the far left column the zygosity, monozygotic or dizygotic. In the middle 2 columns would be the case where there's a single chorion. In the right 2 columns would be the case where there are 2 chorions. Under the single chorion, we see the single amnion, very rare in monozygotic, and does not occur at any appreciable frequency in dizygotic. And 2 amnions at 65% in the monozygotic case, and virtually the 0 cases in dizygotic. So let's just go to the first question at the bottom of this slide. Which has the highest frequency of single chorion? Obviously, we're comparing these 2 here, and 2 amnions. So this would be the monozygotic twins, because there is nil frequency in the dizygotic case. Next, in examining the 2 right columns under 2 chorions, there can either be fused placentas, and we see an asterisk here that takes us below. These result from secondary fusion of the placentas. So it's 25% frequency in the monozygotic, 40% in dizygotic. We're taken to this footnote. And dizygotic twins, the most common type, have their own amniotic and chorionic sacs, but the placentas may be fused as we had seen. With the two placentas, it's 10% frequency in monozygotic and 60% frequency in the dizygotic. So the second question at the lower portion of the slide, which has the highest frequency of two chorions, two placentas? So we see two chorions, two placentas. Obviously, it's the dizygotic twins. So a bit of an exercise in reading tables. Not the most challenging, I admit, but a bit of an exercise there. Continuing then with our discussion, we consider the next case of monozygotic twins. These, as we know, are the maternal or identical twins. They originate from one zygote, and in that case, of course, still a single sperm and a single egg, so they are genetically identical. So sometime after the formation of the zygote, fertilization, we know that the developing cells, the blastomeres, are going to have to separate and go on to differentiate into two distinct and separate, although genetically identical, embryos and fetuses and all the intraembryonic and extraembryonic membranes as we had discussed. But they'll probably share a lot of things because they're contained within the same zona pellucida very early on, and possibly even the same trophoblast cells. So we'll follow through on these variations. It's not always the same, doesn't always happen at the same cell stage, and so on and so forth. So at about the end of the first week, there's going to be a division of the inner cell mass, which is the more common, or the morula, which is less common, into two embryos. So we already know that there is a stage where the cells are going to form tight junctions with each other, and we, I guess, can envision that those tight junctions don't hold steadfast indefinitely in every case. Here is an example of a two-cell embryo following two different lines of separation into two distinct monozygotic twins, so two possibilities. Here we see, obviously, the division of the blastocyst prior to the formation of the trophoblast will generate two distinct blastocysts with the trophoblastic cells and the inner cell mass, all genetically identical, of course. And they go on to form unique embryo, amniotic sac, yolk sac, and their own trophoblastic cell extensions, and so on and so forth. And when they implant, produces twins with separate placentas. So as we remind ourselves of the labor and delivery, we know that the fetuses should be expelled first and then the placentas later. If you have two fetuses and two placentas, what are the guarantees that they're going to come out fetus 1, fetus 2, placenta 1, placenta 2? So there's probably all kinds of variations on that scheme. Anytime there is a variation from that scheme, there's increased risk. So we see there's two amnions, two chorions, and of course two placentas in this case. The other possibility is the division of the blastocyst after the trophoblastic cells form. And we'll see another possibility a little bit farther along in development in a single trophoblast in just a moment that can lead to other anomalous developments. So the inner cell mass is split in half in essence then. So each of those will go on to produce the amnion, yolk sac, and embryo, of course. And then the single trophoblast goes on to develop into the single chorion, the sharing of a placenta, and of course two amnions. Obviously the questions embedded are for you to work with as an exercise to prepare for the exam on this material. Moving on then to figure 728, this diagram is illustrating how about 65% of the monozygotic twins will develop from the one zygote by division of the inner cell mass of the blastocyst, as we had noted. And these twins will always have the separate amnions, single chorionic sac, and common placenta. And if there's an anastomosis of the placenta vessels, one twin may receive most of the nutrients from the placenta. So let's follow on through to see how that might occur. So we recognize this, the division of the blastocysts, the blastomeres of the inner cell mass after the trophoblast forms. This proceeds to enter the uterine cavity and to implant, and with the development of the single common placenta and a single chorionic sac. But each embryo will develop from the inner cell mass, so it'll produce its own amniotic sac, and we've been mentioning yolk sac, but that's not so critical to the discussion of delivery. And the provision of the placental maternal circulation for delivery of nutrients and removal of wastes. So above here we see there's one chorion, one placenta, one chorionic sac, and two amniotic sacs, and obviously a couple of different views at higher magnification of what can occur at the junction of the amnions near the chorion and placenta. So we see a single placenta in each case, and in the lower panel we note one distinction, that the embryonic extraembryonic placental vasculature has an anastomosis. So there's a joining of the vessels at the smaller level of venules and arterioles. So what this means is that, and I'm not certain what the mechanisms are for determining which way the blood might be shunted, but there is the opportunity for one fetus to receive its own circulation and some of the others, and one, of course, to receive less of its own. Leading to this type of a condition here, the monozygotic, monochorionic, diamniotic twins will have the wide discrepancy in size because of the uncompensated arteriovenous anastomosis that we just looked at of the placental vessels. So obviously the blood was shunted from the smaller twin to the larger twin. This produces what is called the fetal transfusion syndrome. Continuing with our discussion of the monozygotic twins, they again are from one zygote and genetically identical. They will have the separate amnions, but only one chorion and one placenta, as we have emphasized repeatedly. Two embryos and one amnion rarely survive because of vascular abnormalities, and there can be other problems that can emerge when they share the single amnion, such as conjoined twins or Siamese twins or parasitic twins. This is figure 730, and it's illustrating how about 35% of the monozygotic twins form from the one zygote, and we're looking at separation, the blastomeres somewhere between the two-cell stage to the morula stage, and there will be identical blastocysts. So we see that separation still within the zona pellucida and two separate blastocysts. This is looking now quite a bit like the dizygotic twin implantation appearance. So the placentas will be separated or fused, and in 25% of the cases there's a single placenta resulting from the secondary fusion, and in 10% of the cases there would be two distinct and separate placentas. In this latter case, the examination of the placenta would suggest that they were dizygotic twins, and that explains why some monozygotic twins are wrongly stated to be dizygotic twins at birth. Everybody looks kind of squashed and funny when they come out, I guess. They're the same sex. You got to wait a while before we pop back into shape and see if they really look identical. But parents will find out eventually, I'm sure. And there's obviously genetic ways of testing. Not that parents would be quite so concerned. So these can go into the two similar directions with a separate chorionic sac, diamniotic, dichorionic, separated placentas, or the diamniotic, amniotic, dichorionic fused placentas, as we had seen with the dizygotic twins, and there'd be the fused chorionic sacs. And we see at higher magnification the distinctions between these. The two separate amnions, of course, and two separate chorions when they're implanted at a greater distance from each other, and when they're implanted close to each other, the fused chorions and two amnions, and of course the fused placenta. One additional instance is farther along in the development of the blastocyst when there is a separation of the developing cells. So in this case, some monozygotic twins will develop, and it is very uncommon where the embryonic disc will result in two embryos within one amniotic sac, as we had mentioned before. So we know we're going to be considering the two anomalies listed previously. The panel A is going to show the complete division of the embryonic disc to give rise to two twins, and they rarely survive because of the problems with the entanglement of the umbilical cords, and obviously that's going to disrupt blood flow. That's always a high risk for mortality. And then panels B and C, as we'll see in upcoming slides, will show different instances of the incomplete division of the disc to show various forms of conjoined twins. So the zygote to the two-cell stage, ultimately to a blastocyst stage with the two-cell preembryonic disc, as we had called it, and for some reason there is a separation or a dedication of one part to proceed toward developing a full embryonic structure, and as well another part to another separate embryonic structure. We're looking at the view that is projected above here, where we see the amnion beginning to develop here, and the two-cell preembryonic disc. And for some reason, there's a division of that preembryonic disc, and we know that this cluster of cells will go on to develop an embryo with the amnion within this amnion and its own yolk sac, of course, and this one as well, staying within the same amnion. So we end up with a single placenta and single chorionic sac, and a single amniotic sac as well. And this is why in this instance there is that risk of the entanglement of the two umbilical cords with compromise to blood flow to both, most likely. If the continued development of the split preembryonic disc is incomplete, the splitting of it is incomplete, obviously there can be conjoined twins, and we know that there's wide variations of where the point of junction can occur, and sharing of vital organs, circulatory systems, and so on and so forth. So we don't go into any detail in our class with that, but certainly the media and most comedy shows are filled with a wide range of examples. The next is the parasitic twins, where there's a complete or near complete development of one of the twins, and the other is typically an incomplete. In this case, it would have to be parasitic, an incomplete, but to varying degrees, development, and obviously a significant amount of contact and sharing of vital organs and structures between the two. So this is a rather quick lecture today. I appreciate that you waited for me and you all came in today. I'll stay for a brief while if there are any questions to hold some office hours. And I certainly hope that all of you are able to volunteer for sometime during our 3-day event or the day before the event to help us set up. There'll be things we'll do here on campus, some things down at the Henry B. Gonzalez Convention Center, day and night. There will be, one of the days is Friday, so that will be a Friday morning where I know that you won't have class, so everybody should be available, right? It is March 30th is the Wednesday, the setup day, through Saturday, April 2nd. And pass the word, whether you're able to help or not able to help, pass the word to other students and encourage them to go, and we'll make UTSA shine in the whole state. Morning. Glad we worked it out, yeah?